Welcome to Chapter 11 of Class 7 Science, Light, Shadows and Reflections. In this illuminating chapter, we'll follow Keshev's summer vacation discoveries about light. We'll explore how light behaves, why shadows form, how mirrors work, and much more. We'll start by understanding different sources of light, both natural like the sun and fireflies, and artificial like bulbs and LEDs. We'll investigate whether the moon produces its own light or simply reflects sunlight. Get ready for exciting experiments that will help us understand the fascinating properties of light. Let's begin with sources of light. Objects that emit their own light are called luminous objects. Natural luminous objects include the sun, stars, lightning, and fireflies. Artificial luminous objects include electric lights, candles, and torches. Objects that don't produce their own light but reflect light from other sources are called non-luminous objects. The moon is a perfect example. It doesn't produce its own light but reflects sunlight, which we see as moonlight. All planets in our solar system, including Earth, are non-luminous. They shine by reflecting sunlight. Modern LED technology represents an important advancement in artificial lighting. These lamps consume less power, are brighter, last longer, and are better for the environment. The Indian government promotes LED use nationwide to save energy. Remember, used LED lamps should be properly disposed or recycled, not thrown in regular garbage. Now let's investigate how light travels. Keshev noticed that light seems to move in straight lines. We can test this through simple experiments. In Activity 11.1, we use 3 matchboxes with holes punched in the same position. When we arrange them in a straight line with the holes aligned and shine a torch through them, we get a bright spot on the screen. But if we move just one matchbox slightly out of alignment, the light spot disappears. This happens because light travels in straight lines and cannot bend around the misaligned hole. In Activity 11.2, we use a flexible pipe to look at a candle flame. When the pipe is straight, we can see the flame clearly. But when we bend the pipe, we can no longer see the flame because light cannot bend around the curve. These experiments prove that light travels in straight lines, a property called rectilinear propagation of light. While in higher grades you'll learn that light can sometimes bend slightly in special circumstances, for now we'll focus on its straight line travel property. Different materials interact with light in different ways. Transparent materials like clear glass and clean water allow light to pass through completely, giving us a clear view of objects behind them. Translucent materials like tracing paper and frosted glass allow light to pass through partially, creating a blurred view where objects aren't clearly visible. Opaque materials like wood, metals, and cardboard don't allow any light to pass through, completely blocking our view. In Activity 11.3, we can test various materials by shining a torch through them in a dark room and observing how much light passes through. We can create a table classifying materials as transparent, translucent, or opaque based on our observations. This classification helps us understand why we use different materials for different purposes: clear glass for windows to see through, frosted glass for bathroom windows for privacy, and opaque materials for walls to block light and provide privacy. When light is blocked by an opaque object, shadows are formed. A shadow is simply a dark area where light cannot reach because it's blocked by an object. 3 things are needed to see a shadow: a source of light, an opaque object to block the light, and a screen where the shadow can form. In daily life, walls, floors, or any surface can act as screens. In Activity 11.4, we explore shadow properties using different opaque objects and a torch. We discover that shadows only form when all three components are present. If we remove the screen, we can't see the shadow. If we remove the object, no shadow forms because nothing blocks the light. If we switch off the torch, no shadow forms because there's no light. We also discover that shadow size depends on the object's position. Closer to the screen gives smaller shadows, closer to the light source gives larger shadows. Interestingly, shadow color is always dark and doesn't depend on the object's color. A red ball and a blue ball of the same size will cast identical shadows. Shadows have been used since ancient times to tell time. In Activity 11.5, we create a simple shadow clock using a stick fixed vertically on flat ground. By marking the shadow tip position every hour, we discover that shadow position changes throughout the day. In the morning, shadows are long and point westward. At noon, shadows are shortest or may disappear directly under objects. In the evening, shadows are long again but point eastward. This pattern repeats every day due to the sun's apparent movement across the sky. Ancient people used this principle to create sundials, among the earliest time-telling devices. Sundials are still used today in gardens and public spaces, demonstrating how ancient wisdom meets modern science. The changing shadows also help us understand Earth's rotation, as the sun appears to move due to our planet spinning on its axis. When light hits a smooth surface like a mirror, it bounces back in an organized way. This is called reflection. Mirrors have smooth, polished surfaces that reflect light in a way that creates clear images. In Activity 11.6, we investigate mirror images using plane mirrors. We discover that mirror images are the same size as the object, appear to be located behind the mirror at the same distance as the object is in front, and are upright. However, mirror images show lateral inversion, left and right appear swapped. When you raise your right hand, your mirror image appears to raise its left hand. Text appears reversed in mirrors. This property is cleverly used in ambulance writing. The word, ambulance, is written backwards on the front of ambulances so that drivers ahead see it correctly in their rearview mirrors. Mirror images are virtual images. They cannot be captured on a screen because the light rays only appear to come from behind the mirror. Pinhole cameras are simple devices that work without lenses, using only a tiny hole. In Activity 11.7, we build our own pinhole camera using cardboard boxes and tracing paper. When we point the pinhole at a bright object, we see an inverted image on the tracing paper screen. Why is the image inverted? Because light travels in straight lines. Light from the top of the object goes through the pinhole and hits the bottom of the screen. Light from the bottom of the object goes through the pinhole and hits the top of the screen. This crossing of light paths creates an inverted image. Pinhole cameras were used by ancient Chinese and Greek philosophers and are precursors to modern cameras. They demonstrate the fundamental principle of photography, capturing images formed by light. The image size depends on distances. Objects farther away create smaller but brighter images, while closer objects create larger but dimmer images. Reflection principles are used in many practical devices. Periscopes use two mirrors placed at 45-degree angles to allow viewing over obstacles or around corners. Light reflects from the top mirror to the bottom mirror, enabling us to see objects that would otherwise be hidden. Periscopes are used in submarines to see above water while remaining submerged, and in military applications for surveillance. In Activity 11.8, we can build a simple periscope using cardboard and two small mirrors. Kaleidoscopes use multiple mirrors arranged at angles to create beautiful symmetrical patterns through multiple reflections. Colored objects placed between the mirrors create endlessly varying patterns that fascinate both children and adults. These devices demonstrate how reflection principles have both practical and artistic applications. Understanding light behavior helps us create tools that extend our vision and create beauty. Let's review our journey through the world of light. We've learned about light sources, both luminous objects that produce their own light and non-luminous objects that reflect light. We've discovered that light travels in straight lines, which explains why shadows form when light is blocked by opaque objects. We've explored how different materials interact with light: transparent, translucent, and opaque. We've investigated mirror reflections and the fascinating property of lateral inversion. We've built pinhole cameras that work without lenses and create inverted images. We've explored practical applications like periscopes and kaleidoscopes. Most importantly, we've learned to observe light phenomena in our daily lives, in shadows that tell time, in mirrors that show our reflection, in camera principles, and in the beautiful patterns created by reflection. Remember to always practice light safety, never look directly at the sun, use proper eye protection, and handle mirrors and electrical sources carefully. Keep exploring the wonderful world of light around you.